Welcome to this week's edition of Good Books Radio. Audiobooks.com is the chief underwriter for Good Books Radio, which is produced by UTRGV Media Services for Rio Grande Valley Public Radio. And now, here's your host, Dr. W.F. Strong.
Welcome to this week's edition of Good Books Radio. I'm your host, Dr. W.F. Strong. Have an exciting book for you this week, The Universe in Your Hand, A Journey Through Space-Time and Beyond by Christophe Galfard. Now, Christophe is quite an impressive man. He has his PhD in theoretical physics from Cambridge University. He is co-author with Stephen Hawking and Hawking's daughter on their first YA book, George's Secret Key to the Universe. Now, this particular book that we're going to talk about today, The Universe in Your Hand, is a wonderful book because it makes accessible the very complex theories of the universe. It's received great praise from like Publishers Weekly, who says it's entertaining and comprehensive. The deft and dazzling imagery makes difficult concepts accessible. Booklist says these probes into the universe will thrill readers and rarely perplex them. It makes, again, the difficult accessible. And another wonderful critique from my 12-year-old son, Dawson, who said that it's awesome, Dad. So there you go, Dr. Galfard. My son says it's awesome.
Well, I'm honored. I will have to meet him one day.
Well, I tell you, it was wonderful for me to hand it to him because he's at that age where he's asking me all of these very difficult questions for me, a novice, about the universe.
So instead of answering, you
I said, "Here's the
book."
Yes. Well, one of the things I found in your book that kind of amused me, you might say, is that when my son was about 6, and he's always had this great interest in the universe, more so than most kids. I think all kids do, but he's a little more advanced in that regard. And he asked me when he was about 6 years old, he said, when you get to the end of the universe, is there a fence there? You know, and your book actually answers that question. And
it kind of does, yes.
Yeah. And another one that he brought up, more recently is also answered in your book, and things like, how long do we have before the sun burns out, and what happens to us when it does? Things like that. So, but I want to begin with something that you kind of, what I would call in journalism, we say that you buried the lead. And I found, just a simple statement that you made way into about the 4th chapter. And you made this statement, and it blew my mind because generally people with your background won't make these sorts of statements. And here you said that you thought within the next couple of decades we would find evidence of extraterrestrial life in the universe.
Right.
How do you come to that conclusion? It's exciting.
That's correct. What's your take on that? Do you believe me? Do you agree with me? Do you want to know why I made that statement?
Well, I will say, yes, I want to know why you made it, because clearly you have a much, much, much better basis for making that conclusion or making that judgment. But for me, I've always had the hope that, yes, given the size of space, kind of like Carl Sagan said, given the size of space, if there's nothing else out there, it's a terrible waste of space.
That's right. You had a good way to put things.
And so I hope so, but I wanted to know why you think that's possible.
Okay, there are several things. First of all, the detection of life. It depends on the kind of life you're looking for. If it is intelligent life, then it somehow does not depend on us. Mm-hmm. We just have to build the right detector to hear some signal, and if we have that signal, we just have to wait for a signal to reach us. Mm-hmm. But it does not depend on us. That could happen tomorrow, today, in a million years. Mm-hmm. It does not depend on us. On the other hand, there is life that may not be able to send what we might call an intelligent signal. In that case, it depends on us. We need to find the right tools. We need to build the right apparatuses to figure out, to see something that we expect would come from some kind of life. Now, many people have asked, but what about life that we know nothing about? We always look at life out there that resembles us? How about a life that has nothing to do with us? And that's a very fair point. But we're not geniuses, we're not gods, in the sense that we are looking for what we know. Yes. The only example of life we know of is the one we have here on Earth. So the first thing is to understand that life we have here on Earth and see what impact that may have on our environment, on the sky, on the atmosphere, and how we could detect that from space. And that's why we're looking for life that kind of looks like the life we know, because we do not know how to do for something we do not know. And we are starting now to have the technology to peer into the atmosphere of distant worlds. That technology did not exist two decades ago. It did not. Now it's starting to be there. And that's why I say that I believe that life is more common than we might think. And so with that technology, maybe within a decade or two, we might be able to spot something. I'd be so happy to live that moment.
Yes, that is exciting. And I was excited to read it because it's so rare that someone with your background will go out on the limb to make such a prediction.
As you said before, the universe is so big. That's the beginning of the book. It's a journey through this immensity so that you can get a feel of it. And the quote from Sagan is perfect. It is true. It is so big, so filled with stuff everywhere, separated by huge emptinesses, but still, there is lots of stuff out there.
Well, let me tell you something I realized recently that gave me an idea of the enormity of space. Is that when I graduated from college in 1977, and I'm now 61 years old, and in 77 they launched, what was it, Pioneer 1?
Voyager
1.
Right, yes.
Yeah, Voyager 1 and Voyager 2, I think, right?
Yes.
And I realized when I was reading something recently that these spacecraft have been traveling all that time, 50 years almost, and they've been traveling all that time, and 40 years, and they have been traveling at 38,000 miles an hour, and they haven't even left the solar system. I mean, or just now entering interstellar space, but they've traveled all that time. And if they were traveling to the nearest star, it would take them 25,000 years to get there.
I'm not sure about 25,000, but hundreds of years. Yes, definitely. You are absolutely right. One of these Voyager, I never remember which one is further than the other, but not by much. But it kind of officially left the solar system last year, meaning the realm of the sun, heading for some other star. And 40 years at an extraordinary speed. The universe is huge.
Yes. And how do they keep going? I mean, are they powered by something? My understanding was that these, what I'm curious about is how do they still send back photographs and things, so what keeps them powered?
Yes, so they don't need power to shoot away from us anymore. In space, there is no friction, so once you have some speed, you keep it. And what would require some energy would be to slow down, but they don't need to. They shoot straight ahead. Now, they do indeed send back some pictures, but that's technology from 40 years ago. So it's amazing. They managed at the time. The computer inside is much less powerful than an iPhone, and still it does send back some pictures. So that if I remember correctly, that there is an atomic battery in there which may last some years still. When they didn't have all that technology that we have today, the engineers were extremely bright.
Yes, that's right.
They still are, though. I'm not saying the other way around, but they had to figure out ways for things to keep going despite the lack of batteries and stuff.
Well, given the enormity of space, and given that we only have 5 billion years left of our sun,
that's not much.
So here's another question. My son asked me, how soon will we within 3 centuries have interstellar space travel?
Well, that's a very difficult question to answer.
That's what I said.
There is this project by Professor Hawking with Yuri Milner that was announced a couple of weeks ago, last week, where they intend to send a spacecraft to another star, which is interstellar travel.
Right.
That would take years to get there. To send a robot or something, that may well be within our reach today. It's difficult, but not necessarily impossible. On the other hand, if your son wants to travel to another star, I'm afraid he's going to be disappointed unless there is really some kind of extraordinary breakthrough in the years to come. That's not going to happen within our lifetime. That's not going to happen.
Well, for us to ever really travel interstellarly, aren't we going to have to find something like, warping the space-time continuum? Are we going to have to find a wormhole? Are we going to have to find some extraordinary means of that we don't currently understand to achieve
Definitely. Maybe either the ones you mentioned or some different ones altogether that we don't even have names for right now. Imagine a 1,000 years ago, if you could travel back in time and you would meet somebody from back then and tell them, that we have built airplanes. They wouldn't even know the names or the concept. They would have birds, yes. But
yes.
To imagine that a huge metallic something could fly, that's something that was beyond their imagination. I'm pretty sure.
I still think about that when I'm on a plane. I say, how in the world do they get this thing off the ground? But I think that all the time. We've only had flight for about 100 years, and yet we have airports everywhere and thousands of flights a day that are really safe on the whole.
That's right. But let me add something for your son, not to be too disappointed.
Okay.
One of the problems, indeed, with space travel like this, interstellar space travel, is the distances, and hence the time of travel. You would want, ideally, I guess, a spaceship to get you to your destination before you're dead. That's something you might want to be sure of. So you have several ways to shorten the time. One is to use the things you said, warping space-time, like wormholes, shortcuts in space and times, meaning that you don't have to actually travel the real distance that separates you from these faraway places. But there is another way, and the other way is to go real fast. That's one of the chapters in my book, I believe, where if you are on some kind of spaceship that travels at a significant fraction of the speed of light, then your time slows. Actually, your time stays the same, but it is not the same as the one of people who stayed on Earth. Meaning that a year for you could correspond to 1,000 years for people who stayed on Earth. And that just depends on your speed. You, of course, would require an enormous amount of energy to reach those speeds and get your time to slow down. But using such extraordinary velocities, you could reach faraway places before you're dead.
Yeah. Okay.
Let me show you why that is something that happens all the time right now. You may have wondered about people saying that when you look at the stars out there, you're looking at the past, that some of the stars might be dead, and we actually still see them, which is correct. And the reason for that is that light does not travel instantaneously. It has a velocity. It's fast, but not that fast compared to outer space. But light does not age. If you were to transform yourself into light and shoot away in space, you wouldn't feel the passing of time. Time would not pass for you. Time would stop. And that's the reason why the images we receive now that were emitted by faraway sources like stars on the other side of the universe, these images as they arrive to us now are exactly the same as they were when they were emitted. They didn't age. If you send a postcard to someone, a postcard that travels for 1 billion years, you won't recognize the postcard. It would be destroyed. Light does not. change. It is always the same. And so when you receive an image from a star that is a billion light years away, that image was emitted a billion years ago. So you see the star exactly as it was a billion years ago. To have a look at how it looks like now, you'd need to wait for that image to reach us. And you have to wait a billion years for that to happen.
Fascinating. And it's a beautiful thought, too.
I like to compare astronomers looking at the stars like to postmen who receive postcards from all the four corners of the universe, and you just have to classify them by date of emission.
Well, is it possible to, based on what we know now, is it possible to go faster than the speed of light? Is there anything that can do that?
Well, that's not. It is possible for something to move faster than light, yes, but it is not possible for anything to communicate something at a speed faster than light. I don't know if you get the distinction between the two. The distinction is that if something is moving away from you right now at a speed that is faster than light, you will never, ever be able to know about it.
Okay.
Because nothing from there can reach you.
Yes.
Ever.
Yes.
So there's no point in trying to use that. That's not going to happen. You don't have any information that can travel at a speed faster than light. That's ruled out by what we know right now. But there are some things that do travel faster than light, in a way. For instance, when you when you look at the stars, for about 80 years, 90 years now, we've known that faraway stars, faraway galaxies look as if they were moving away from us. That's what people have called the expansion of the universe.
Right.
That everything that is far away, like really, really far away, moves away from us in every direction.
Right.
That makes you feel at the center of the universe because everybody's trying to move away from you as if you had a bad stench. But that's not actually what really happens. What really happens is that all those galaxies and faraway stars, they don't actually move by themselves. They are like us. They don't move. What does change is that the distance that separates us from them stretches. It is the distance that stretches. So wherever you are in the universe, wherever you look, if you look far away enough, because distances stretch, you will feel like everybody is moving away from you. We shouldn't take it personally from Earth. It's true for everywhere, everywhere.
And is that because
of that expansion, you may have some distant planets that look like they're moving away from us faster than light, but we will never be able to see them.
But is that because of the Big Bang that they're moving away?
Well, yeah, that's one of the reasons. Although that may not be an explanation, but in the theories we have of, let's put it differently. That's without giving it a reason. That's what we see in outer space.
That's what you see. Okay.
Yeah, we see that things are moving away from us, and from that knowledge, from that experimental knowledge, people came up with this extremely bright idea. Now I can show you how bright scientists are sometimes. Seeing that all the galaxies were moving away, they set up conferences, drank coffee, discussed with each other, and came up with this extraordinary idea that if everything is moving away from us now, then in the past it must have been closer. I think it took them about 1,000 years to figure that out, because it seems stupid said like that, but it did change everything we knew about our universe since Aristotle. For 2,000 years, the universe was thought to be static, not moving, not changing, and suddenly it was not anymore. And if you go back in time as far as you can, you end up with this idea that the universe must have started somehow, must have had a beginning, must have had a Big Bang in its past. So it's the other way around. It's the experimental verification of the fact that faraway galaxies move away from us that led to the idea that the Big Bang must have existed in the past.
Now, you make a point in your book that if you go far enough out in space, at least past the known light universe, that there's still something out there. What is there?
Yeah, so you remember a few minutes ago we were talking about receiving postcards from everywhere in space.
Yes.
So the further the source, the further back in time your image comes from. Now, if the universe started with a Big Bang, there must be a place where you can't, a place in space that is a limit somehow, because if the Big Bang happened, say 13 point something billion years ago, then you cannot receive anything that was emitted before that.
Right.
But the limit we have is not that one. The limit we have is the first moment in the history of the universe when light was able to travel. This was not the case when our universe was in its infancy. There was so much energy everywhere. The universe was so dense that light could not travel freely. That was not possible. But then it expanded, cooled down, and became transparent. The furthest thing we can see in space using light is that transition, is a moment in the history of our universe when it became transparent to light. And that is the wall at the limit, at the end of the visible universe. And as I say in the book, there is indeed something behind, going back all the way up to the Big Bang itself, and that's a stretch of about 380,000 years of the history of our universe that we will never, ever be able to look at using light. And that's where those gravitational waves might come in handy.
Well, you said before we got on the air, you were telling me about the gravitational waves because we were discussing the Gravitational Wave Center here at University of Texas, Rio Grande Valley, and you were explaining that this gives us a second tool. So you want to run with that now that we're on the air?
Sure. The fascinating thing about looking at the stars and the universe that's out there is that since forever, we've only really had one tool at our disposal, which is light. We cannot receive any other signal but light from outer space. We have been when you look at things, you receive light. When you use detectors to telescopes, you receive light. You collect light from outer space. But this situation has now changed. Since September last year, we have a new tool at our disposal, a new detector that detects not light, but something else, something whose existence had been predicted by Einstein about a century ago, and had remained elusive until now. But now we are able to detect something that is called a gravitational wave. These are they are fascinating even in their names. They are ripples that propagate through space and time. Our eyes are not built to detect these. Nothing in our body can detect them. But some scientists did manage to build detectors that actually made contact with such waves last year. And as I was telling you before, this means that I truly believe that 2015, just because of that, or just thanks to that, will remain in textbooks for at least 1,000 years from now.
That's amazing. That's an amazing thing to say.
We do. We do now have a new eye, a new way to look at the heavens and see what's lying up there. It's very hard to tell what discoveries might be made thanks to these. But there will be. That's absolutely certain.
Well, is it possible that in looking for extraterrestrial life, that we're looking at light and we should be looking at gravitational waves?
I wouldn't go that far. There is something related to the cost of emitting some signal. The energetic cost of emitting gravitational waves is immense. Just to give you an idea of how immense that is, let's go back to that detection in last September. What they detected was the collision of two black holes. They merged to form just one black hole. In doing so, they did not emit any light at all, but they emitted gravitational waves. They basically lost 5 times the mass of the sun in 5 milliseconds. That's 1/200th of a second. And that corresponds, that's about the same as 50 times the power of all the stars in the universe combined. And these waves have been propagating through space and time for a billion years to make a very, very tiny movement, which is a billionth of a millimeter, that was felt by those detectors. So it's extremely expensive to do that, to communicate. Light is much easier.
Well, I would think that such a massive event would have produced a really big wave, you know?
It is big, that's the thing, because, okay, let me give you an example. Were you to be next to that collision, you wouldn't see any huge firework of light, you would see nothing, but you would be, the wave would propagate through you, and that would make your size vary by about 5%. I don't know how tall you are, but let's say that's a couple of inches. Let's say 1 inch, okay, for you. 5% for a human, that's strange, but that's not that impressive. But it's true for a star as well. If there is a star nearby, its size would wiggle by about 5%. And that can be hundreds of thousands of kilometers. And for the Earth, for instance, that's hundreds of yards of changes. If the Earth had been next to that.
Next to that, right, yes.
It is a huge amount of power.
Now, my understanding is that they want to measure, well, it may already exist, but I remember hearing some years ago that they wanted to put like satellites in space 1 million miles apart to capture these waves. Is that right?
That's absolutely correct. The project is called LISA, like LISA. For this stands for Light Interferometer Space Antenna, and that's a crazy project. It's exactly the way you said it. And it's 3 satellites, 50 million. That's about 30 million miles apart in space, and extremely stable, staying there. 30 million miles is big. Just to remind you, I think in miles, the diameter of the Earth should be something around 8,000.
Right.
I'm not sure about my conversion, but it's something like that. Let's say 10, even if it was 10,000. We're here talking about 30 million miles apart, linked with laser beams that would detect infinitesimal changes in the distance separating those things. It should happen. I think this LIGO detection gave them a boost.
Yes, I think so.
I hope your son will be able to work on that one.
That would be great. That would be great. Well, I'm sorry we are out of time and probably out of space too on the recording system. But it's been great talking to you. As always, that's a great thing about talking to an astrophysicist is that there's always more wonderful questions to be asked and to be probed. But our time is limited, unfortunately. So I want to recommend your book, The Universe in Your Hand, to everybody. It is by Christophe Galfard, PhD, and your PhD is in astrophysics?
In theoretical physics.
And what's the difference?
The difference, well, astrophysics is more looking at the difference may be tiny somehow, but theoretical physics is more like trying to figure out the laws of the universe. The difference might be, my supervisor was Professor Stephen Hawking, and that's the kind of theoretical of things that theoretical physics is about, trying to figure out what the laws of nature are. Astrophysics might sometimes be more specific to one type of star or a black hole or things like that.
Well, when you work with a man who's known to be one of the great geniuses in history, is that kind of foreboding?
Well, he gave me so much. He taught me so much, and that it's just pure joy.
Yes.
I've been with him several times in Texas, actually, and to College Station and some other Texas A&M universities.
Yes.
And the joy he has in spreading his knowledge and to teach and to try and figure out how the universe began, it is it catches you.
Yes.
You
So he's very
I'm
nurturing and
really thankful.
he's very nurturing and inspirational intellectually, I'm sure, right?
Indeed, for your research and even for your life. The way he's happy and living a wonderful life despite everything, that's some inspiration for us all, I think.
And he has great humor, I understand. He's very funny.
Yes, that's absolutely true.
Well, thank you so much. Enjoy your tour in America, and hopefully you'll be doing more, and we can talk to you again in the future and with forthcoming books.
That would be with great pleasure. Thank you very much, Dr. Strong.
You're welcome. Have a good day. That's it, ladies and gentlemen, for this week's edition of Good Books Radio. I want to thank our underwriter, audiobooks.com, where your first book is free. Here's hoping that all your books are good reads.